Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving into a fascinating blog post, Introduction to Stochastic Calculus. It's a beginner-friendly exploration, focusing on intuition and calculus-based derivations, avoiding the heavy probability theory you might find in a textbook. Excited to get started?
Absolutely. I've always been intrigued by stochastic calculus, but the formalisms often seem daunting. What's the core idea the author is trying to convey?
The main goal is to show how stochastic calculus, specifically Brownian motion and Ito calculus, emerges naturally from the physical world. It starts with a very relatable example. Pascal's triangle. You know, the one with the binomial coefficients?
Oh yeah, I remember that from combinatorics. What's the connection to Brownian motion?
Well, the number of paths to reach a certain point in Pascal's triangle corresponds to the binomial distribution. The author then cleverly shows how, by taking the continuous limit of this discrete model, we get the normal distribution, which is the foundation of Brownian motion. It's a beautiful connection.
I see. So essentially, they're building up Brownian motion from a simple, discrete model. That's a really intuitive approach. What about Ito calculus? How does that fit in?
That's where things get really interesting. Because Brownian motion is nowhere differentiable, standard calculus doesn't work. Ito calculus provides a framework to handle this irregularity. It's a whole new set of rules for integration and differentiation, tailored to the random nature of Brownian motion. It involves a special chain rule, Ito's lemma, which includes a correction term that accounts for the roughness of Brownian motion.
So the correction term in Ito's lemma is crucial because of the non-differentiability of Brownian motion? That's a key takeaway, right?
Exactly. That extra term is what distinguishes Ito calculus from regular calculus. It's a consequence of the fact that the square of the Brownian motion increment, dw squared, is not negligible, unlike dx squared in standard calculus. It's approximately equal to dt.
That's fascinating. And what about applications? The blog post mentions several, right?
Yes, the applications are incredibly diverse. In finance, Ito calculus is fundamental to option pricing models like the Black-Scholes equation. In physics, Einstein used Brownian motion to prove the existence of atoms. And now, there are even applications in machine learning, using stochastic differential equations to generate new samples. It's truly a powerful tool.
That's amazing. So it's not just theoretical, it has real-world impact across many fields. The author also mentions Stochastic calculus, doesn't he? How does that differ from Ito calculus?
Yes, Stochastic calculus is another approach to stochastic calculus. The main difference lies in how the stochastic integral is defined. Ito calculus uses the left endpoint of each interval in the Riemann sum approximation, while Stochastic uses the midpoint. This seemingly small change leads to different results, especially in the chain rule. Stochastic calculus preserves the standard chain rule, which can be advantageous in certain contexts, like physical systems where noise is tied to physical continuity or symmetry.
So the choice between Ito and Stochastic depends on the specific application and the nature of the noise involved? That's a crucial point to remember.
Precisely. The author provides a clear explanation of the conversion formula between the two, allowing you to switch between them as needed. It's a really comprehensive introduction, covering the key concepts and applications in a clear and engaging way. I highly recommend checking out the original blog post for more details and the accompanying code examples.
Definitely. This has been a great overview. Thanks for breaking down this complex topic so clearly. It's given me a much better understanding of stochastic calculus and its applications.
My pleasure. And thank you for listening to Tech Bytes and News. We hope you enjoyed this deep dive into the world of stochastic calculus. Join us next time for more exciting discussions on the latest tech news and breakthroughs. Goodbye.
Bye-bye.